When most of the dry matter has been removed from the water by coagulation and sedimentation, the water is filtered. In order to remove further dry matter, the water flows through a grid filter. To remove organic dry matter specifically, the water subsequently flows through an activated carbon filter. Since both filtering processes use the same basic principles, both filters are modeled in the same way. The only difference will be that the grid filter removes dry matter in general, both inorganic and organic, whereas the activated carbon filter removes organic dry matter specifically. In the filtering process, the water flows through a layer of filter material of a given thickness Z. The concentration of the matter that has to be filtered out decreases exponentially with the thickness of the filtering layer, as shown on this slide. The interesting part in this formula is how the parameter lambda is computed. This parameter describes how effectively the filtering process works. Since the filter removes dry matter or organic dry matter from the water, this matter remains in the filter. This remaining matter in the filter is called filter load, denoted by the symbol sigma. For every filter, there is a maximum load. If this maximum load is reached, the filtering capability is lost. This maximum load is called saturation load, denoted by the symbol sigma s. Using these parameters, as well as some value for the initial effectiveness lambda 0, we can determine the parameter lambda as shown on the slide. Now we have to determine the initial effectiveness lambda 0. In reality, this value is determined empirically by experiments. In our example, we assume that our filter can initially filter out 90% of the matter contained in the water. That is the ratio between the desired concentration of the inorganic or organic dry matter at the outflow of the filter and the concentration of the matter at the inflow is 0.1. Based on this assumption and the thickness of the filtering layer, we can determine lambda 0 as the negative ratio of the natural logarithm of the concentration ratio and the filter thickness. However, we still cannot determine our value of lambda. In order to do this, we still need the current load of the filter as well as its saturation load. The saturation load is defined as a constant. Now, how do we compute the current load of the filter? This is done by integrating over time the difference between the initial concentration of the matter in the water and the concentration at the outflow, divided by the thickness of the filtering layer, multiplied by the velocity at which the water passes the filter. The last thing that we need to know is the velocity at which the water passes the filter. This velocity is computed by dividing the volumetric flow rate through the plant by the surface area of the filter. Now we've got all equations to generate the model as well as the parameters that characterize the filter. This filter would work pretty well now. However, after some time it would be of no more use, since it would be saturated up to its saturation load. Therefore, before the filter reaches its saturation load, it has to be purged. This is typically done when 80% of the saturation load has been reached. We do not want to model that purging process in detail. We will just simulate this purging process by resetting the value in the integrator block that computes the load of the filter. Such a reset can be done using an external trigger. In our case, we define that the reset is to be performed at the rising edge of an external trigger signal. In order to generate such a signal, we use a switch function block that, depending on its input, forwards one of two input values. Here we can define that when the middle input signal exceeds a given value, for example 80% of the filter's saturation load, the upper input is forwarded, otherwise the lower one. U2 is the middle input signal. Now we define some threshold, and when this threshold is exceeded, the signal of the upper input is forwarded, else the lower one. If the upper input's value is now larger than the lower one, then we are able to generate the desired rising edge of the integrator's reset input. Now what signal is used as input to the middle input port of the switch? Which value do we have to check? It is the filter load, which is the result of the integration process within the integrator. Now we can define if the middle input, if the current filter load exceeds the given threshold, the upper value is forwarded or else a lower one. This means when in turn the integrator's value is reset, the input condition of the switch does not hold anymore, and the switch again forwards the lower input with the lower value. Therefore, the switch again is ready to deliver a rising edge the next time the filter load exceeds 80% of the saturation load again. Implement a subsystem in your model representing a grid filter using the formulas presented in this unit. The grid filter filters out dry matter. Update the concentration of dry matter in the bus using its newly computed concentration. Additionally, update the organic dry matter in the bus. Up to now, organic dry matter has not been treated separately. This will be the case in the activated carbon filter. Therefore, we have to use the correct value of organic dry matter. Therefore, set the value of organic dry matter to 1/3 of the value of dry matter. Additionally, implement a subsystem that represents an activated carbon filter. It will be an exact copy of the grid filter with only a few exceptions. The activated carbon filter will filter out organic dry matter, thus computing the new value of this parameter. Therefore, the computation of the organic dry matter as 1/3 of the dry matter, which has been done in the grid filter, is obsolete. Additionally, some filter parameters are different as seen on the slide. Instrument your model at will.